about giving our LoRa devices eyes and ears. He's actually going to show us. So I'm looking forward to that. Please raise the roof for Jongboom!
Thanks, Justin. Awesome to be back. Who was here in 2020? Good. I didn't bring a sheep this time, but I did bring something where we can actually do some audience participation. So we're going to be building something at the end of this talk together and actually testing that stuff out. So really, really excited about that. So I'm Jan. If someone would ask me how many years of experience I have with the Things Network, it would be all of them, because I met Johan and Winke even before TTN got started, been to every TTC. And the Things Conference is even more special because at the conference in 2020, 2.5 years ago, we launched Edge Impulse, the actual product, general availability. And you can see that on the graph here, all the way at the left. There was 0 projects at TTC 2020 created on Edge Impulse. Today, that is over 110,000 projects, real ML projects, people using data and machine learning together to draw conclusions directly on the sensor edge, which is mind-blowing, truly mind-blowing. And hopefully after this session today, there will be a few hundred more of these projects because you're all so inspired and you want to go add some eyes and ears to your actual sensors. So first of all, I want to congratulate, I think, the ecosystem. So I was looking at the device repository, and we have 576 devices in there today. And for me, I started doing LoRaWAN back in 2014, 2015. We tried to source some very basic peer motion sensors in 2015, and there were about 0 actual available. Lots of really nice brochures, but nothing you can actually buy, and that's something that has changed a lot. I think just that there's actually a stand here at the Things Conference where you can just go and buy sensors is already truly amazing. And the over 1 million registered devices on the Things network, or through the Things industry, are something that I think has shown that we as a community, right, have grown into an actual viable ecosystem, not a toy or something you try around, but somewhere where people actually add value. However, when I did a bit of a drill down into what these sensors all do, I found that 33 of them are environmental sensors. So that's 1 in 20. 14 of them are peer motion sensors. And a staggering 184 are temperature sensors, or have a temperature sensor on board. And that makes me a little bit more sad, because how many temperature sensors does a man need, right? And when you look at kind of more complex stuff, there's 0 visual sensors. There are 0 stuff with a camera, and only 3 that actually have a microphone on board. And they don't use that microphone to actually do really complex stuff or recognize scenes or nothing. It's literally just loudness sensors. And it's kind of weird, right? Because the world, everything that we see around us is really made for people. Lots of information in the world is visual, right? I can perceive it with my eyes, or I can hear stuff happening. And what we do with these sensors is to try and convey information from the real world and bring it into the digital world. And through that, we need to do some translation of how we see the world, right? Either through our eyes or through our ears, into something that the machine can actually detect. So stuff that is easy for us but hard for sensors, but still doable, right? I can buy sensors that tackle these use cases today, probably from vendors that are sitting here in the room, are stuff like, are there people in the meeting room? Now, if I look at a meeting room, it's very easy for me to see if there's a person, yes or no. So we try to approximate that through, for example, a peer motion sensor. And that sort of works, but then falls apart the moment that someone doesn't move enough. Actual case that we built in 2015 in Telenor. We try these sensors to actually approximate the world for us. Similar, water hammer in a steam pipe. So if too much pressure builds up, you hear a really loud bang. You can sort of detect that through a loudness sensor, one of these 3 sensors that you have that I had on the previous slide. But it's sort of a poor approximation. Maybe there was a different, very loud sound happening at that time. And then there's also cases that are easy for people, but are currently impossible for these sensors, right? Is there a crack in the style? Yes or no? Like manufacturing quality control. for me, if I look at it, and for you hopefully as well, if you look at this tile, you see, OK, there's definitely a crack in there. OK, awesome. Next. Try go on DigiKey and buy a crack sensor that does visual stuff. It doesn't exist, right? It's way too, it's too complicated, and it requires kind of real understanding of the world. Similar, with a loudness sensor, I can detect loudness, but if I want to do something that is, whatever, I want to detect elephants in Africa, I can't go to AVNet and say, well, give me one elephant sensor, please. Right? So these things are easy for us and require an understanding of the real world, but are impossible with the kind of sensors that we have today. So part of the reason why I founded Edge Impulse. So I've been doing IoT for quite a while, and I was sort of disappointed, right? Like people told me there's going to be billions of devices sensing information in the real world. It's going to be awesome. And what do we have? 184 fucking temperature sensors in the marketplace, right? I want to have true, actual insight in stuff that is happening. And for that, my devices need to have eyes and ears and understand this in the same fashion as we understand the world. And you might think, well, we have really small battery-powered devices. Like, where am I going to even stick a camera? Or it's going to be too expensive? Or, how do I actually write my application logic in a way that that can convey this super high, basically big amount of data need to be processed on the sensor edge? Like, how am I going to do that? It's actually not that bad. Like, first of all, the hardware has become really cheap. So, for example, if you want to add eyes to your device, this Hymax targets, an HM0360, is actually a VGA monochrome, like not something you want to put in your smartphone, but a VGA monochrome sensor, including their complete processor. So it does all the image preprocessing. Literally, the only thing you get out of it is a buffer, is a frame buffer, right? Just $4.39 on DigiKey if you buy 3,000 of them. This is something we've integrated for a customer. Similar, on the audio level, MEMS microphones have made stuff really, really tiny. You can basically fit it in here. And really cheap. So a MEMS microphone, this one from TDK, goes for about 80 cents in volume on DigiKey. Then step 2 is, OK, well, why is the very first project that people built in an IoT system, is it always a connected temperature sensor? It's because it's really, really easy to build something like that. You take a temperature sensor, and it just gives you a reading, and then you relay that value over to the internet. And a lot of devices, even complex one with lots of sensors, are basically that. They just do a reading, maybe it's CO2 levels or gas or whatever, and relay that over the network, and that's your connected sensor. If you think about, OK, well, think of an example as water hammer detector, right? So let's take one of these sensors that has a microphone or loudness in it. And now I write an application, so I take my input, my sound wave. My rules are very simple. If it's above 90 decibels, then I want to send an alert out. Now, we as humans can reason about this, right? I can go to Johan and say, Johan, write me a control loop that does this. Really easy. If I now need to do, based on I now need to want to detect an elephant trumpeting, it's going to be a lot harder, right? Because, OK, I can't just have a simple threshold value. I need to find a certain pattern in the sound wave, really, really complex stuff. So something that's really hard to do by hand. Machine learning, however, like swaps this around. So rather than say, you provide me the input and you come up with the rules, and from that we get an outcome, whether we need to send something. In machine learning, we say we swap this around. So we have an input, we have our outcome. So this was water hammer, this was not water hammer. This was water hammer again, this was not water hammer. And then we let the computer figure out these rules. And as a computer is a lot smarter than us and doesn't have like the constraints of a very tiny human-sized brain, these rules can be much more complex than these basic thresholds. And this is kind of the real way of how we can enable this, right? Because rather than having to figure out this whole control loop ourselves and write these algorithms ourselves, we let the computer do that. We just throw a bunch of data in there, and then the computer comes up with these algorithms. And then step 3, like once we've done that, it's just like any other application. So you pass in sensor data. You get probabilities out. This was a water hammer. This was not a water hammer. This was an elephant. This was not an elephant. This is a crack in a tile or not. And then you just relay that over LoRa back to TTN or TTI. And if you think about it that way, actually, this whole idea of machine learning, it's super complex, and I don't even know where to start, and data, and I need a mathematics PhD, becomes much easier. It's just a different way of writing your control loop. Rather than thinking about, like, oh, I'm looking at my data, and my thresholds are like this, and I need to configure it that way, you say, OK, well, I get all this data, I tell exactly what was happening at this point, and now I let the computer figure out how to separate these two events. And from that, it's just another application. So that was in 12 minutes, basically, a summary of why I think that machine learning is really interesting and why you should add that. Then, of course, the question, wait, but. So here's a couple of debunkings. So first of all, doesn't machine learning require a lot of compute? You know, I want to build a small device. I'm running this on my microcontroller. Yes and no. So yeah, the beautiful part of what we do with these small devices is that very often we just have a constrained use case, right? If you think about state-of-the-art computer vision models like YOLO v5 here, they can detect thousands of objects over 100 classes in a single frame. Yeah, you need probably a GPU or a neural processing unit to run this on your device. Not going to fit on a small battery-powered sensor. But very often we don't have this problem, right? We have constrained models, we have constrained problems, and through that we can use constrained models as well. So, for example, just a very simple classification, do I see a person in this room, yes or no? The amount of compute, the difference in amount of compute is about 1,000x here, because the problem is 1,000x less complex. So, whereas for YOLO v5 you probably need to run this on a GPU to get any decent frame rate, this very basic classification problem of, hey, is there a person in the room, can run on a Cortex M4. So really interesting. And embedded devices are already very powerful. Like even if you think about something that's in the market today, like a cheap $2 microcontroller, very often has a floating point unit, actually has vector extensions. So it's really good at vector math. And what is machine learning? It's in the end, it's just a bunch of vector operations, just vector math. So these are actual examples of pipelines. So doing audible event detection, like Waterhammer, takes about 84 milliseconds to analyze 2 seconds of data on a Cortex M4. And it can run on under 20 kilobytes of RAM. Multi-object detection, so something that I want to not just know, do I see a person, but actually where in the frame do I see this person? And are there multiple persons? There's a demo at our booth on the face detection. We can run this on a DSP in over 10 frames per second. Running in this case, this model is 190K. And we can even drop that down. If you make it even less complex, even drop that down to something like a Cortex M4. Second is, like, doesn't machine learning require lots of data? Also true. But here, the constraintness of the problem helps as well, right? If you want to do Waterhammer detection, it's very simple. It's either Waterhammer or not. With a few hundred samples, you build a data set up that is actually good enough. And then we've done some other work within Edge Impulse to add stuff like transfer learning, where we say, hey, actually, think about a keyword spotting demo, right? We've already trained a base model on 1.2 million spoken words. Now, what does the machine learning model need to learn in that model is, first of all, decomposing what voice is and what a keyword is. And we figured, well, the first couple of layers of that network are going to be the same regardless of the keyword that you're going to have. So we just let you fine-tune the model on the keywords that you're interested in, so it can be completely custom. And this way, you lower the data requirements a lot. So again, constraint problems require less data here as well, so it helps us a lot too. In the demo that we'll actually have about a minute of data in a little bit, so stay tuned. And also, even if you have a problem where you say, well, for example, I have an event, and this is the case a lot in anomaly detection use cases or predictive maintenance, there's a lot more cases where you have good data, so the machine was functioning correctly, then you have bad data of, there's a fault happening. So if you have a case like that, we can even deploy an anomaly detection model where you say, well, you don't have any anomalous data, or maybe a few samples to verify that the model works. And now just tell me when something out of the ordinary happens. And this is really cool, because now you can do this with only good data, and that makes it a lot more flexible. So what about battery life? Very true. Like, lots of the sensors that we have are battery powered. So think about it this way. Machine learning is nothing more than just a fancier control loop, right? And other than that, your whole application stays the same. You still need to do careful application design. If you're going to run your camera 24/7, doing inference all the time, yeah, you're going to run through your battery really, really quickly. But you wouldn't do that on a normal sensor. So this is something we built with ERNAS. This is a nature conservation camera. So what we do is we say, well, we have an external trigger, a peer motion sensor. Once we see motion, that's the moment that we actually enable the camera, snap a photo, and then try and see what is in front of the frame. So you could do this way through a peer motion sensor if you have a camera. You could also do a loudness detection system before you actually go run classification on the audio signal. And then, well, wait, isn't machine learning really, really hard? I'm just an IT developer. How am I going to do this ML stuff? Well, we've gone through that journey. I was an IT developer, not a trained machine learning engineer. So we built Edge Impulse, my company, as the place, sort of like the Things Network that democratized LPWAN, democratizing machine learning aimed at embedded engineers. So if you're an embedded engineer or you're making devices, you should feel right at home. So we'll guide you all the way from initial data collection all the way to deployment. As said, we have 110,000 real ML projects created by the community. Really cool. A couple of customers that we have on here, so this is really used for real production systems as well. And this is going to make it a lot easier. And for that, I have a demo, and we're going to be building a model together here in the last 6 minutes. So you don't need to feel fearful about machine learning. After this talk, you can do this as well. So yeah, so from zero to model, basically the 3 steps you need to do. First, get data. A machine learning algorithm is as good as the data you put in it. So we have ways to upload data if you already have audio, images, whatnot. If you have a UART port on your device, awesome, with a little data forwarder so we can get raw sensor data straight from there. You can use your mobile phone, which is what I'll be doing to do some data collection in a little bit. Then you'll build your model. So we support audio, images, radar, motion, basically anything under the sun. You can plug in your own signal processing pipeline if you have that. And then finally integrate it into your firmware. And it's just like any other library. It's a bunch of math, essentially, what you get, written in C++. You pass your sensor data in, you get probabilities out. That's all there is. So let's go build something together. All right, so this is an Edge Impulse project. So we have our data here. And I figured it would be really interesting if my device, I got a Cortex M4 with a LoRa shield here, if this device could understand a small sentence. And we are at the Things conference. So I figure if all of us would yell TTN together, that's the thing that this device will go and recognize. So to do that, first of all, we need to get some training data. And I can do this from my phone. So there we go, I connected my phone. And now what I need you guys to do, when I put my hand up, you all need to yell TTN. We're going to do it 3 times. Yeah? Anyone who doesn't do it need to give their drink ticket to me. All right, so I'm going to do 10 seconds, and we're going to do 3 of these TTNs, guys. Amazing. All right, so we're uploading. So here is going to be our 10-second sample. So as you can see, we have 3 good spikes. And let's split that up, because we have 1-second samples here. Really easy. Split sample already finds it. And let's listen to one. I don't think I have audio routed. Beautiful. Amazing. So we split it up, and this way we build our data set. And for these kind of small models, I did this yesterday with my team, basically adding, whatever, 30 samples of TTN together is enough to actually get a model that actually converges. So I've done this work for you. You can actually follow this whole thing on your mobile phone. The moment that you sign up for Edge Impulse, this is the first thing that you get prompted. You can go from 0 to trained model in 10 minutes. True. So we trained up this model. Gets about 97% accuracy. which is pretty amazing. And from that, I can compile this down. So this model runs in 180 milliseconds to analyze a second worth of data. So we still have 80% of our time left on device. And once we compile this, we get a C++ library out. And you integrate that into your application like any other library that you get from a sensor manufacturer. So I've done that on my board here. Let's open the TTN console. And let's open my serial port. All right, so now we're listening. So now we need to do this again, and then we're going to see if my device actually sees all that. Yeah? Ready? Amazing. Schedule for transmission. I don't know what the console is doing here, but big shit. Can we do it one more time? Let's refresh the console. Let's clear that out. There we go. TTN detected one time, and a good logo in here. So that's literally how easy it is. Go build your model, collect some data. We mix in some noise and unknowns, and from that point, we actually have, an actual working keyword spotting model here, running on a Cortex-M4, relaying stuff to the internet. So we've done some demos earlier this year or a year ago with Lacuna Space, where we actually used a detection system to count birds and then relay that over a satellite back to Lacuna. Like, how fucking cool. All right, one more time. Amazing. Oh, man, so fun. Next year, I'm going to dress up Johan in a sheep costume again. So recap. So the world is really made for human senses. And we can try and build poor approximations through buying peer motion sensors or loudness sensors and sticking them to our sensor. But much better is just go with the flow, right? Actually add some eyes and ears to your LoRaWAN device itself. It's by far the easiest way of getting a true understanding of the world and getting a good insight into what is happening around your device. And one thing that I also hope you've learned from this is that machine learning actually doesn't need to be data centers full of compute. It can actually be super tiny. The model that we just trained for a commercial customer who makes headset, we actually run this on a Cortex-M0. Like, truly amazing. With that, I want to thank all of you for being here. And awesome to be here, and I'll see you guys next year.
Thank you so much, Jan. It was a great demo.
Thanks, Justin.
Thank you so much. Demo gods smiled upon this demo here today. That doesn't always happen, so we're happy about that. Now, we are going to continue with another talk, but in the meantime, if you've started to feel peckish, lunch has started to open. You need to get a token from the Mousite booth to grab lunch. Sorry, not from the Mousite booth, from next to the Mousite booth. Lunch will be on in the next couple hours, so no rush for that. And then you go to the food court to use the token. And at 5 p.m. today, we'll have some closing words by Wienke and Johan, so that's going to be good. Up next here on stage, one of my favorite people in the world is going to be presenting, and she's going to be talking about real-life LoRaWAN and basically transforming industries and communities using that. She came all the way from Australia. I'll introduce her in a second, so see you back then.